Dear friends, welcome back. So this is a wing. It's a symmetric wing we are discussing in the last lecture, right? Do you want to see how it's going to fly? So does it fly? Is it going to fly or not if I throw this as it is, right? So let us have some marking on this. Like as I told you, this is of 0.23 meters span. I mean the chord is 0.23 meters and a 1 meter span, right? I request Himanshu, my TA, to help me with this. So sorry, he is my researcher, right? So this is approximately 0.23 meters. You can see here this is 0.23 meters or 23 centimeters is the chord of this. So what will be the aerodynamic center for this configuration?
5.75.
Yeah. So this is about what? It's a rectangular wing. So the chord remains same. Lambda is 0 in this case. So what you have is 2/3 of
0.25 of C.
yeah 0.25. The C bar will be CR, and the aerodynamic center will be 0.25 times of this.
This chord length.
Yes.
5.75.
So 23 by 4 is approximately 5.75. So this particular marking here is 5.75. Say this is my marking. What about this side? Can we mark it again? So this again is 5.75 meters. Okay. So if I draw a line representing the mean aerodynamic chord of this, can we do that? Yes. Where is that? So, see. Can you hold this? You come this side. So this line, which is connecting the aerodynamic center from tip to tip, right? So this line is going to represent the aerodynamic center of each and every aerofoil and the entire wing, right? Now let us mark this as AC of wing, right, which is at a distance of 5.75 meters centimeters from the leading edge of this wing. Okay, this is your aerodynamic center. Now let's measure the weight. Is approximately 150 grams, right? And let us throw this as it is, right? Let us see how what it's going to do. See, it just flipped, right? Shall we do it again? I'm just throwing it. Right? It is flipping, right? It is continuously flipping. Okay, let me do a small magic or a trick. Say this is a molding clay, which I borrowed it from UAV lab here. Right. So I have attached this molding clay to this rod here, which is connecting the wing, right? So now let us see how it's going to fly. Should I throw it? So it's better, right? So as soon as I add this molding clay to this, it started gliding. it's not flipping the way it behaved in the first case. Okay. Let us take another wing. Okay. So this is a cambered aerofoil, it's a wing of 1 meter span. So both of these have same planform geometry, if you can see. So both the models have the same planform geometry, but what is the difference between these two wings is a cross sectional profile. We have used different aerofoils. So the one in my right hand is with a symmetric aerofoil, and the one here is with a cambered aerofoil, right? The one in my left hand, you can see it's a cambered aerofoil, right? Now I have already attached some clay here, molding clay, to this particular configuration, and I am going to throw this. And again, both of them are with similar chord. Let me mark down the aerodynamic center of this. So it is again 23 centimeters chord, right? It's a rectangular wing. So the mean aerodynamic chord is again 23 centimeters. So 23 by 4 will be my aerodynamic center, which is 5.75 approximately. So this is my aerodynamic center. So how about this side? So I have marked aerodynamic centers on the other side. So let us join these aerodynamic centers. Okay. This line represents your aerodynamic center. It's a cambered aerofoil, right? The wing is with the cambered aerofoil. See the glide? Plays a crucial role in this. Yes. So what is the reason it started flying as soon as I attached this clay, right? What must be the reason? So we haven't changed the wing, right? All we did is shifting the CG. That means, say with this clay, how to measure the CG in the first place? CG of this wing. Either you need to have two balances like this. Say you place it on one balance here, another you have another balance at a offset, right? You take m1 x1 plus m2 x2 divided by m1 plus m2. Right? That is one way. Other simpler way here is, in our case, see, so about CG, the model will exactly balance, right? Let us say if you take a horizontal rod and if you place this model on that horizontal rod, so about CG, this model will be balanced exactly, right? So that location you can consider it as CG location, right? So in this case, about this location, the model is exactly balanced, right? In this case, this is the location about which the model is exactly balanced, and this location is along the aerodynamic center of this wing. So if I am shifting the aerodynamic center towards the CG of the wing towards the aerodynamic center, then it started gliding. So say in this case without any clay, right? So the CG is somewhere here, right? So almost close to this point. this is at this particular location. The CG in this case is at this particular location, which is aft the aerodynamic center here. That means for a, let us say if I make CG 2 ahead of this aerodynamic center, right? What to do that? What should I do? I mean, if I want the CG ahead of this aerodynamic center, I need to add more weight here, right? Yeah. Say there is some more molding clay. Now the CG is at this particular location, right, which is ahead of this aerodynamic center. Okay. Okay. So during the, if I fly, if I try to glide, I mean throw this wing with this particular CG setting, let us see what happens. See, there is a nose down, right? Immediate diving. There is no glide, it started diving down, right. See, with this particular CG setting, this model started diving down, right. Let us say I reduce this clay, again I am bringing that CG back, right. What I am trying to do now is bringing close to aerodynamic center here. Now it is behind the AC. So right now I am able to balance this model about the aerodynamic center. See, this is my aerodynamic center. I am able to balance this model. Now let us see how it is going to behave. It is able to fly. Shall I repeat this? See, it is a glide, right? Now let me remove this clay again. So let us see where is the CG, location of the CG. It has definitely shifted backward, right. So this is the point about which I can balance this model. So this is your CG location, this is your CG location right now, which approximately this is your CG location, and this is aft this aerodynamic center. Right. If I throw this, so it flipped, it is a somersault, right. So let me do it again. I am not trying anything different compared to earlier cases. It is automatically flipping. See, let us see whether it repeats or not. Whatever the angle that I am trying to do, but it will flip. So it can't be 2 ahead or 2 behind. What do we infer from this? right? It should not be two ahead or two behind. That means you need to figure out what are the limits of this CG. And right now we do not have a tail, right? What happens if we add a tail? How far this CG traverse can be allowed? We will discuss this in this lecture. Now to do this, when the CG is close to this aerodynamic center, in this case for a wing alone configuration, so that too for a cambered aerofoil, right? So we see a smooth flight. Smooth in the sense, so it was actually the intended path, right, which I was trying to, or say it should be the intended attitude of the flight. So it should glide. That's the whole idea why I am throwing. But when the CG is behind, it started flipping. Okay. So what is the difference in between these two? In the first case, it has something called, we call it as a stable flight. In the second case, which is unpredictable, at the same time unstable here, right? It started flipping. And in the other case where the CG is ahead, again it is diving down. So we checked in one of the flights where the CG is near to the aerodynamic center, we witnessed a stable flight, which let us say we consider it as a reference. And in the other cases, we witnessed an unstable or offset flight conditions, right? So what are the parameters that govern this stable and offset flight conditions? Fine. So we use something called stable, right? Stable flight. What is stability? Right. So stability is a property of a system or the nature of the system to come back towards some reference that you consider when it encounters a small disturbance about that reference. So this reference in our case or in general is a equilibrium. So now we should talk about when we say a stable flight, first we need to understand what is stability of a system, right? Let us talk about stability. Now with the help of the concepts of stability, let us see how do we design the tail and how do we find the limits of the CG traverse and what should be the size of the tail, yeah, and the offset between the tail and the wing. So all these parameters comes from this stability analysis of the system, right? So what is stability? It is a tendency of the system to attain equilibrium once disturbed from it, right? What is this equilibrium again? It is the state of the system about which resultant forces and moments are balanced. So that means the forces and moments are balanced, or there are no resultant forces and moments. Forces and moments are balanced. That means sigma f bar is equals to 0, sigma m bar is equals to 0, right? So about equilibrium of a system, the forces and moments are resultant forces and moments are 0. There are no resultant forces and moments. So there are many examples you might have studied in your earlier courses where you consider a simple pendulum. Right? What are the equilibrium points of it? That is minus pi by 2 and pi by 2. Right? At theta is equals to, say this is your 0 inclination, this is your pi by 2 and this is your minus pi by 2. Right? At this, so there are two equilibrium points of a simple pendulum, right, about minus pi by 2 and pi by 2. Now consider the case where it is at minus pi by 2. Right. So this is your pivot point O, and let m be the mass of the system. Now you display this mass by an angle theta, where L is the length of this is your theta, and you displace this mass to an angle theta here. This will still remain L, the length will remain constant here. So as soon as you leave it, what happens? This bob will try to come towards the equilibrium, this mass will try to come towards equilibrium, and because of its inertia it will start accelerating, and till here it will accelerate, after that it will decelerate and attain a orientation theta prime where the velocity, terminal velocity here is 0, right, and then it will start coming back, right, and it will go forth and back, right, and finally attains a equilibrium if there is enough friction in the hinge as well as there is a friction in the surrounding atmosphere, right, air friction or a fluid friction. So that means once you disturb this particular object from its equilibrium, right, it will try to come back towards its equilibrium. Right. So this particular equilibrium is known as stable equilibrium. That means the system is finally attaining its equilibrium. Right. So let us consider a case where there is no air resistance, and say this connecting rod has negligible mass and there is no friction. So you are performing these experiments in a vacuum chamber. So what happens is this will keep oscillating. We can say the system still trying to attain the equilibrium, but it will not reach the equilibrium because there is no resistance, there is no damping to that oscillations, right. So there is no damping in the system, it is trying to oscillate about this equilibrium, right. So the system, although the system tries to come back towards this equilibrium, but you can't say the system is stable in that case. Why? Because it is ultimately not coming back to that equilibrium, right. After a while it should come back towards that equilibrium, right, but it has a tendency to come back towards, but it is not attaining that equilibrium here in this case. Even in that condition we can't say that the system is stable, right. That means, so when you are talking about stability, you are talking about two conditions here. One is the tendency to come back towards this equilibrium, and finally over a time period you are looking at the behavior of the system and commenting whether the system is coming back towards that equilibrium or not. So there are two phases here, there are two cases for this stability. One is the initial case is static stability. Right. So at any instant you see the pendulum is here trying to come back towards its initial equilibrium position. So that talks about your static. At any instant, does it have this tendency or not? That is a static stability. The study about such condition is the static stability. Whereas if you are looking at the time history of this motion and say how long it is going to take to come back towards its equilibrium. Say if it has to come back towards its equilibrium, what should I do? How should I increase the damping? Or what should be the time to halve these oscillations? So the study, the study related to this time history of this motion once disturbed from its equilibrium is the dynamic stability. So dynamic stability talks about the time history of motion of the system once disturbed from its equilibrium position. Now consider this, see we have another equilibrium point which is at pi by 2. So assume that the pendulum now is at the other equilibrium point which is pi by 2, right. So this is similar to this case, right, where you are holding a stick, right. So at some point, yeah, this is stable here when you make it like when you place it on the table vertically, it is stable. When you place this pen or the marker vertically on this table, right. So this is also an equilibrium point, because if there is a resultant force, there will be a motion, right, and moments it will try to rotate, resultant moment, but here the resultant force and moments are 0. That is why it is at rest right now. But whether this position is stable or not, let us say if there is a small disturbance, it has attained a new equilibrium, it haven't came back to its previous equilibrium, right. Let us say in the other case, if I hold at the top of this marker, say if I give some external force, right, it will start oscillating and coming back towards its equilibrium. So this particular equilibrium is a stable equilibrium. So the one at pi by 2 is a unstable equilibrium, because it is not coming back to its initial equilibrium once disturbed from it. The same thing here. So you see right now, since I am holding it, now I can vary the friction here or the frictional force. So say if I disturb this, it may not go down. Say if it is a proper hinge, it will definitely, any small disturbance will definitely take it away from this particular equilibrium, which is an unstable equilibrium here, right. Now what are the conditions here for which, so in this case, in case of a pendulum, see if the CG is beneath the hinge point, so this is your CG, right. If your CG is beneath the hinge point, it is a stable equilibrium. The equilibrium in which the CG is beneath the hinge point is a stable equilibrium. The equilibrium in which CG is above the hinge point is an unstable equilibrium, right. So similarly, do you have something in the aircraft, right, but in this case the CG and the hinge point are in the vertical axis. So what happened to the aircraft? What is the, so we have lift from the wing, lift from the tail, right, and CG acting at some other location. The hinge point and CG are in the straight line here in both the equilibriums, right, in the vertical axis. So but in that case there is an offset where the CG as well as the aerodynamic forces act, right. So we need to see where should I locate the CG so that the system is automatically stable, right. See here you are not controlling the system here. Once you disturb from its equilibrium, there is no need for any external control, it will automatically come back towards its equilibrium. It will automatically come back towards its equilibrium once the perturbation is done, once the external force is removed from it. So here the system will come back towards its equilibrium automatically once there is no external force acting on it, right. So another example that you may consider is, take a bowl. So these examples you might have studied already, right. You take a ball placed at this location, at the bottom location of this ball, it is a concave ball, right. Now you displace this to a particular location here, either this side or this side, it will start moving towards the initial equilibrium. So in this case the resultant forces and moments are 0. So once you displace and leave it, it will start oscillating about this particular equilibrium, right. So it will start oscillating about it and finally attains this equilibrium, which we can say it's a stable equilibrium, right. So if you take a convex bowl, if you place a ball here, what happens is, as soon as you perturb this, it will either go this side or this side, right. It will not come back towards its equilibrium. So here in the first case we are not controlling any, we are not imparting any external forces here, it is automatically coming back towards its equilibrium. So similarly the UAV should have the initial the tendency to come back towards its equilibrium, then we can say it is a stable UAV, right. So even while varying the CG, what we witnessed is the stability of the system is changing, right. So let us see how the stability changes as the CG varies. So again in this pendulum case, mass, right. In this particular equilibrium location where it is minus pi by 2, right. So at this equilibrium point we say this is a stable equilibrium, right. If there is a friction, enough friction that helps this pendulum to come back towards its initial equilibrium. So in this particular case we considered it as a stable equilibrium. Why? Because it is attaining its actual equilibrium. But how? What is helping? Why not in the other case? Right? Yes, okay. mg, even gravity is there in the other side as well. There is a component of this mg, right, mg sin theta and mg cos theta. So this mg sin theta is what driving it towards its equilibrium, right. But this force about this particular point, hinge point, is creating a moment, right. This is into L, mg sin theta into L is a moment that is created about this hinge point, right. That means there is a moment that is restoring its equilibrium. That moment is known as restoring moment, right. In order to have this equilibrium stable, I mean if you need to say if a system have to be stable, then there should be a restoring moment. So we know aircraft have 6 degrees of freedom here, right. You can translate as well as rotate along the 3 axes here of this body frame. So it can translate along x, y, z and rotate along these 3 axes. So the rotation along the body x axis is known as roll and pitch and yaw, right. We have roll, pitch and yaw of the system. Okay. So the pitching moment is about y axis. Now say let m be the moment here, which is given as half rho v square s cm into c bar. Half rho v square s is the force dimensions of the force and c bar is the dimensions of the length. So force into length is a moment, it's a moment arm, you can say c bar, and cm is the non-dimensional pitching moment coefficient. Right. Cm is a non-dimensional pitching moment coefficient. So Cm is twice the pitching moment divided by rho v square s into c bar. Okay. Now this is a moment that we are talking about. Even in the pendulum there is a moment, right, because of the force. So this is the moment because of the aerodynamics. So there in the pendulum case we have that moment due to gravity. Here we have a moment, this Cm is a moment that is due to the aerodynamics here. So consider the CM variation with angle of attack. Since we mentioned it's a aerodynamic moment, so these aerodynamic forces and moments depends upon the angle of attack, right. Let us consider this variation of the CM with angle of attack. Right. So let us say this is for the entire aircraft or a UAV, entire UAV. So say in the first case you have a UAV which is, so let us say this is your UAV A, right. Say this is your UAV B, right. So what is this particular point? So for this UAV B you have CM variation, this blue line represents the pitching moment coefficient variation with angle of attack. For the UAV A, this pink line represents the pitching moment variation with angle of attack. So what is this particular condition? This is a increasing alpha, okay. So this is your positive and this is your negative. What is positive pitching moment? So we discussed, right? Right hand thumb rule, stretch your thumb along the positive axis, right? Positive axis and the corresponding curl of, the curl of your fingers will give you the corresponding positive moment. So so this CM is about, pitching moment is about y axis. So stretch your thumb along the positive y axis of this UAV and the pitch up is considered as positive and pitch down is considered as negative, right. Now what is this alpha, what is this point? So you can see at this particular alpha you say the moment CM is 0, that means there is no pitching moment for this particular angle of attack, right. Do you accept this? So which means the moments are 0 or a pitching moment is 0. CM is 0 means of course M is 0. That means it's a equilibrium point. If there is imbalance in the force, that creates a moment, but when the resultant forces are equal, there is no moment here. So about this point there is no moment, right. Okay. We can consider this as equilibrium. So this is your equilibrium. Now let us say there is a sudden increase in the gust or the wind which has increased the angle of attack, okay. So this particular point alpha E equilibrium is perturbed by alpha prime. The new angle of attack is perturbed by an angle of attack, perturbed by wind, and the resultant angle of attack at that instant is alpha prime. Right. So this alpha prime, if I consider the UAV A, what happens because of this change? There is a pitching moment, it is a positive pitching moment. That means the aircraft will have a nose up, right. So this is your positive y axis, say this is your positive y, this is your positive x and this is your positive z. So stretch your thumb along the positive y and the curl of your fingers will give you the corresponding positive rotation here. So this pitch up rotate motion is considered. Pitching up is considered as positive, pitching down is considered as negative, right. So with the increase in the angle of attack, there is a increase in the moment. Initially at this particular angle of attack where the resultant forces and moments are 0, right, you have 0 moment definitely, because that is the definition of equilibrium here. So as the angle of attack increase, there is a change in the moment and the change is in the resultant moment is positive, which means there is a pitch up moment, right. So initially say this is your angle of attack, this marker represents the angle of attack, right. So this is V infinity and this is your angle of attack, the angle between them. So because of a small change, so this is the trim condition, let us assume, because this is your alpha E, because of a small change there is an increase in the angle of attack, small disturbance, external disturbance. So this angle of attack, increased angle of attack for a aircraft with that pitching moment curve, let us say that is a UAV A, right. So this curve represents the pitching moment variation with angle of attack for UAV A. So for such UAV what happens, so this increase in angle of attack is increasing the pitching moment, that is nose up moment, it further increases. So, this further increase due to this nose up, it further increases the angle of attack, right. So, that means let us say this is your alpha double prime. Now, the increase in angle of attack due to pitch up is alpha double prime. So, for this UAV you have Cm prime, Cm double prime, okay. That means there is a further increase in the pitching moment, which further creates a nose up and further increases the angle of attack. So, alpha double prime or triple prime will result in a Cm triple prime. This is alpha triple prime. Okay. That means you are moving away from this particular equilibrium point. See here, this is your equilibrium point, you are moving away from it. Now, in the other case, say for the same UAV A, if there is a disturbance that has reduced the angle of attack, say. So, initially this is your angle of attack, say at equilibrium. Now, this disturbance has reduced the effective angle of attack here. So, this reduction in angle of attack for this particular UAV with this pink curve, right. So, will result in a, so say this is your alpha prime in the subscript, right. So, this results in a Cm prime in the subscript, okay. Now, which means your pitching moment is negative here, right. There is a negative pitching moment which is a nose down. That means this will further decrease the angle of attack. If the aircraft will do a nose down automatically, and which eventually result in a reduction in angle of attack further. So, alpha double prime, so this will again right decrease the pitching moment or gives a negative pitching moment, okay. So, that negative pitching moment further will reduce the angle of attack. That means it will go to alpha triple prime in the subscript. So, this will further create a pitch down moment. So, in either case, if you follow a UAV with this pink curve, you will end up moving away from the equilibrium once disturbed from it. Similar to that of a pendulum case, where you have an equilibrium, but it is at minus pi by 2, sorry, right. If the CG is about the pivot point, then the equilibrium is not stable, the system is not stable about that particular equilibrium, right. So, on the other hand, if you look at this blue curve, so look at this blue curve that represents the variation of pitching moment with angle of attack for a UAV B. So, this alpha prime, when there is an increase in the angle of attack, there is a Cm prime in the subscript, that is a negative pitching moment, right. So, let us say there is a disturbance that has increased, this is my equilibrium alpha, right. So, there is a disturbance that has increased this alpha, but with the UAV with this particular blue curve, this change in the alpha will induce a nose down moment here, Cm is negative. So, this nose down moment will decrease the angle of attack, right. That means you will start moving towards this equilibrium point, it will start decreasing the angle of attack, right. So, similarly, if the angle of attack is decreased, say this is your trim angle of attack or the equilibrium angle of attack, right. If the angle of attack is decreased due to the disturbance, what happens? So, this reduced angle of attack will induce a nose up moment. From this curve you can see this reduced angle of attack will induce a positive moment, which is nose up. That means the aircraft will pitch up and go back towards its, that means pitching up means it is increasing the angle of attack, that means you are moving from here to here, right, moving towards your equilibrium point. So, what do we infer from this discussion? That means for a UAV to be statically stable, right. So, this Cm versus alpha has to be negative. The slope has to be negative. Here the change in Cm, dCm with d alpha is negative, whereas the dCm by d alpha in this case is positive. So for unstable aircraft this change is positive. For a stable aircraft the change in pitching moment with alpha is negative, right. So dCm by d alpha is equals to should be less than 0 or negative. And by the way, what is this moment about? This moment we are talking is about the CG, but due to aerodynamic forces, right. And so we are starting with static stability. So we discussed that there will be two phases of the stability, static and dynamic, right. Initially we are arriving at the mathematical conditions for static stability. If the UAV has to be statically stable, the variation is in pitching moment with angle of attack has to be negative, right. The slope of the Cm alpha should be less than 0, okay. So this is a necessary condition, but is it the sufficient condition? Let us say you have the Cm variation with alpha, the blue one, negative. Let me draw a parallel curve for this, right, with a negative slope but passing through origin here, okay. This is your Cm versus alpha. So this is UAV C, right. This is the third UAV, okay. So still even in this case with the change in angle of attack, say this is your equilibrium here, that means you are trimming your aircraft at alpha is equals to 0 angle of attack. So at this equilibrium, about this equilibrium, when there is a change in angle of attack, increase in the angle of attack, there is a nose down moment that will take you back towards your equilibrium and vice versa. But what is the trim for this UAV? It is at 0 angle of attack, because you can't trim at positive angle of attack, you will get negative moment. So let us let us have a curve which is offset to this. So these three are parallel, okay. So this is your UAV T. So in this case where is the trim? Is at negative angle of attack. This is your negative alpha, right, alpha negative in this direction. So the trim is negative here, alpha is negative, that means, but we witness CL is equal to CL alpha, CL naught plus CL alpha into alpha. When you have negative angle of attack, you are actually reducing the lift CL, that means you will not be able to sustain the weight, right, at this particular angle of attack. So it is an inefficient flight if you have it, right. The whole idea is to generate lift at minimum velocity and the minimum conditions, power requirement conditions, or the minimum, minimum fuel consumption, right. So although you have Cm alpha curve, Cm alpha negative for even for this UAV D, but you can't trim this at a positive angle of attack. So the Cm naught, what is Cm naught here? Here it is 0, here it is positive. What is Cm naught? Cm at which alpha is equals to 0, right. So here it is positive. This is for blue curve, this is your Cm naught. Cm naught. So for yellow curve, this is your Cm naught is 0, and for this brown curve it is your Cm naught, which is negative. This is greater than 0, this is equivalent to 0, okay. So for this to trim at positive angle of attack, I need to create an offset here, right. To create that offset for a flat plate, this is how it will be. We will witness for flat plate what is going to be the CM, right. So, in order to trim at positive angle of attack, you need to have, so this is your trim at positive angle of attack. Trim is an equilibrium, right. So, in order to trim at positive angle of attack, you need to have positive CM naught, right. So, when there is, this is your negative CM naught, this is your positive CM naught. This positive CM naught will help you to trim at positive angle of attack. So, CM naught has to be greater than 0, CM alpha should be less than 0, or it should be positive for sufficient. So, necessary and the sufficient condition for statically stable UAV.